Thank you all for joining us for this webinar on a timely topic of hydrogen. My name is Milind Dev. I'm a professor of chemical engineering, University of Utah, and also director of Energy and Geoscience Institute, EGI, at the University of Utah. So I'll probably take about 35 minutes, I think, 35 minutes. And then I think there will be plenty of time for a discussion, question, answers. There has been a lot of talk about hydrogen lately. There seems to be significant movement, momentum towards hydrogen technologies. So I'm going to provide an overview of where things are and where things stand with respect to the different aspects of the use of hydrogen. So this is my talk outline. I will just give a very basic introduction to hydrogen as a fuel, what its properties are. Then look at the production of hydrogen. Even though there has been good amount of interest in natural hydrogen lately, very little is known about the existence of natural hydrogen, and I'll talk a little bit about that. Then talk about the production methods for hydrogen. The most common ones, steam methane reforming, electrolysis, and then a few other methods that are not that common. Transport of hydrogen, we'll just talk about that briefly. When hydrogen is not going to be used on site, it needs to be stored. So we'll talk a little bit about storage. In a circular type of a system, the generated hydrogen is used for other purposes, or also for power generation, for again creating electricity. So we'll talk about some aspects of that. Other hydrogen end uses. We just completed a study of water use in hydrogen life cycle, because there is some concern about the use of water in hydrogen, and then we'll close with some conclusions. As many of you know, hydrogen is considered an energy carrier and not an energy source, even though, as I said, with the finding of natural hydrogen in Mali, there is some possibility of producing hydrogen as an energy source. It is very attractive as a fuel because it has a very high energy density, as you can see on this plot. 120 megajoules per kilogram compared to about 50 megajoules per kilogram for most of the hydrocarbons, including natural gas, is about 56 megajoules per kilogram. But of course, it's a light gas that has a density of 0.084 kilograms per meter cube. And as a result of that, its volumetric energy density is much lower than regular fuels. As you can see, again, on this plot, that the fuels that we do use commonly, diesel, gasoline, jet fuels, all of these are very high on the volumetric density basis. Hydrogen is very high on the gravimetric density basis, but low on the volumetric density basis. I just put down the critical properties here. They're more relevant when you're thinking about liquefying hydrogen, or because if it becomes supercritical, then you'll not be able to liquefy it regardless of the pressure. Starting with this introduction, there have been a lot of colors given to hydrogen depending on the source of hydrogen. Green hydrogen, which is hydrogen produced from electrolysis when the electricity comes from renewables. So this will be zero net carbon, or very low carbon hydrogen. Blue hydrogen is when hydrogen is produced from fossil fuels, like steam methane reforming, but CO2 is captured and stored. Gray hydrogen is when it is produced from steam methane reforming, but there is no carbon capture. There are a few other colors that even I was not aware of when I started doing this compilation. So maybe as more sources of hydrogen become apparent, we might run out of colors eventually. Anyway, so pink hydrogen is electrolysis of water. When electricity comes from nuclear, turquoise is when it's hydrogen pyrolysis, brown is from coal gasification. Yellow is when you have electricity, but electricity comes from various sources, which is what we currently have in the grid. And then white hydrogen is the natural hydrogen or from industrial sources that is as a byproduct. Anyway, so we should just be aware of this because this provides some basis for what the carbon footprint of the produced hydrogen is, because one of the big incentives, of course, for the hydrogen economy is to have either a zero carbon or a very low carbon fuel. So one of the contemplated hydrogen life cycle use is basically to make hydrogen using renewables like wind or solar, use electrolysis then from that electricity to make hydrogen, store it. One of the possible storages is in salt caverns, and this is the least expensive large-scale storage of hydrogen that's available. And then you would, at times that you do need electricity, you would use that for power generation and generate electricity. So this actually would stabilize the supply of renewables. So you would essentially, hydrogen would be used, looked at as an energy storage material. So let's start with sources of hydrogen or production of hydrogen. As I mentioned to you, there has been a good bit of interest in natural hydrogen lately, and we've done a significant review of the literature in this area. And these next 3 slides are from my colleague, Dr. H. Setayama, who's working on this project. So this is from a review article, recent review article, and you can see that there are a lot of areas around the world where natural hydrogen has been found, including in the United States. There are not very many dots here in South America, not probably because it doesn't exist, but because there hasn't been enough attention or discovery on this continent. But yeah, you do see that there is, and then these sources of hydrogen vary in concentrations from fairly high concentration. This is, of course, in Mali, in Western Africa. I'll describe this in a little more detail. There is the big, almost pure hydrogen was discovered, but other sources here have varying concentrations from that 100% to maybe 5% or 2%. So this can be quite varying. And this hydrogen is called golden or white hydrogen. An orange hydrogen is when stimulated by injecting water. So if this is produced in our lifetime, not geologic lifetime, then it can be thought of as a process for producing hydrogen from natural processes. Of course, the advantages are that it potentially, because there are not that many discoveries, it's a low carbon footprint and low cost source that is available, but there are a lot of challenges associated with it. The geologic attributes that actually create a source of hydrogen are not fully understood. Production technologies have to be developed. We don't know if the technologies that we use for natural gas can directly be adapted, especially because hydrogen has different material interactions, and then separation, if it is associated with other gases, will be a big challenge as well. So here are some of the mechanisms for the creation of hydrogen. As you can see, one of the 3 main mechanisms that have been proposed are radiolysis, where radioactive elements react and generate hydrogen. The most common mechanism that has been understood to be the source of hydrogen is serpentization, which is the reaction of ferrous to ferric in the presence of water to make hydrogen, and then deep-seated hydrogen, which comes from the mantle, which is a little bit rarer. And then hydrogen does have several loss mechanisms. That's one reason why it's not as commonly found as methane. And then the different traps that can exist for the trapping of hydrogen. Anyway, so this schematic shows the different processes that Dr. Satayama looked at, and including this over-maturation of organic matter that could also is postulated or hypothesized to be one of the mechanisms. Just a quick background on this Boreka Bogo well in Mali on the Western Africa. This is estimated to contain about 5 million tons of almost pure hydrogen. The map is shown here. It's the composition of this particular gas on this scale is shown here. The Mali well falls here. There are other wells that are shown on this map as a ternary diagram with methane, nitrogen, and hydrogen. This particular well is also associated with methane accumulations, but they are in different layers along this depth, indicating that the mechanism for accumulation, cogeneration is very different, but even accumulation and traps are different. And we are studying that now in detail to figure out under what conditions this would accumulate and what are the geologic attributes that would facilitate the accumulation of hydrogen in natural systems. Anyway, so that's, I think, ongoing and is a promising area of research as we look at natural sources of hydrogen. Hydrogen production in the United States is a fairly established industry. I showed you just in the slide before that this particular well in Mali had about 5 million metric tons. That's estimated. The current annual production in the US, just to put that in perspective, is 10 million metric tons. Most of it is used almost on site for petroleum refining, about 70%, and then 21% for fertilizers and other uses after that. But most of this hydrogen is produced where it is needed and consumed. But this map basically shows where the significant facilities are, mostly Gulf Coast here, a little bit of accumulation in the Chicago area, then California, and then scattered on the western side. But this is a fairly well-established industry, most of which is produced using steam methane reforming, which consists basically of two reactions, the reforming reactions and then the water gas shift reaction that produces hydrogen. This is a highly endothermic reaction, so it takes a good bit of energy to make hydrogen from this pathway, but it's still the most common and, as I said, the most well-established method. So let's just dig down into what this consists of. The next few slides are from this fairly recent 2022 report from Department of Energy, NETL, National Energy Technology Lab. So this is the schematic. The process itself is quite complicated, as I'll show you a little bit later. But basically, natural gas is pre-treated first, comes into the reformer, combined with air, basically, for providing the energy that is needed for the process using combustion. And then there are some heat recovery systems. So because it's a fairly sophisticated process, the heat recovery systems are built in. There is and the gas is cooled, some separation goes through some separation, and then hydrogen product is recovered at this stage. I'll define two things here. The effective thermal efficiency is heating value of hydrogen plus net power that is used in making the hydrogen divided by the heating value of the fuel that is actually supplied to the process, and the coal gas efficiency is the hydrogen heating value divided by the fuel heating value. So obviously, if hydrogen is to be produced for a low carbon means, you have to capture CO2, because as you saw in the reaction, CO2 is one of the components in the process that is produced during the reforming process. So it needs to be separated. So there are now established technologies for separating CO2 from, it goes through several steps actually, this methyl ethanol amine absorption followed by this CANSOL unit. This I think is a commercial process. Shell, I believe, has this technology. And then CO2 is recovered and then compressed and then either sold as a product or stored, sold as a product or stored. So this upstream process for making hydrogen is combined with this downstream process of capturing CO2 in this hydrogen production with CCS. As I mentioned, the processes themselves can be quite complicated, as is shown in this simulation diagram. In practice, this can even be more complicated. And you can see that there are several units that are combined. There is extensive heat recovery unit, and then there is a stripper absorber system for recovering carbon dioxide. So that's with methane as the feedstock. There are other feedstocks that can be used for making hydrogen as well. Coal is there is a commercial process in a couple of places around the world for using coal to make hydrogen, not as common as, of course, SMR, steam methane reforming. Biomass processes are being developed. In fact, even in our department, Professor Vitti is working on technologies for taking biomass to hydrogen. And then you can actually use a petroleum residue or waste for making hydrogen, and then the entire cycle then of using that hydrogen for various means. So when you have good heat recovery system, here is, this is from, again, that report. It shows that the effective thermal efficiency and the coal gas efficiencies are in the 75% range for steam methane reforming without carbon capture. With carbon capture, that drops by about 5 to 7% in that range, maybe 10%. And then autothermal reforming is a slight variation of this, where the energy that you require for steam methane reforming comes from auto-oxidation of methane. And so that has comparable efficiencies to SMR without, so this is with CCS and this is without CCS, but this is what the autothermal process brings to reforming. And then as you go to more complex feedstocks, the efficiency drops. But generally, I think these are still slightly higher numbers in practice. For installed capacity SMR, I would say that the efficiencies are more in the 65 to 67% range. And this is something that I have verified from several other reports on operating steam methane reforming plants. What about costs? So as you know, there is a hydrogen earth shot that aims to make low carbon or carbon with CCS less than $1 per kilogram in the next 10 years. So this is again from this report. I don't think the recent cost increases in methane as well as some of the inflation costs are built into this. So I would say that, so this is in dollars per kilogram of hydrogen that includes transportation and storage. And it lists it as $1.06, but I would again think that it's in the more in the 160, 170 range, given the current cost of natural gas and other costs of energy in the process. But this gives you a good feel for what the costs are and how they increase as you go from the basic process to carbon capture and sequestration, the autothermal process, and then as you go to other feedstocks, there is a little bit of a, since this is an established process, there is less of a spread in this cost compared to these other processes. There are only a few operating plants with CCS currently in the world. There is one in the US in Port Arthur, one in France, and one in Canada. And then there are a lot under development. And these have fairly significant capacities, as you can see, 200 million standard cubic feet per day. Most of these are SMR. Some of these now, the ones in development are with autothermal. And then the capture technology, the acid gas recovery, AGR or CO2 capture is shown here. The ones that are operating at around 50 to 60% CO2 capture. The ones that are in development are aimed for higher percentage CO2 capture, which of course would increase costs as well as energy requirements. Electrolysis to produce hydrogen is not as established as reforming, and this technology is still being developed. There are different types of electrolyzers. Alkaline are the most common and have been used for other applications. So polymer electrolyte membrane, PEM membrane process that's shown here is the next most common. And then the solid oxide high temperature process, which can be used for, which can be combined with nuclear power production, is also being discussed a lot for electrolysis to produce hydrogen. But in general, the energy efficiency in most of these processes, again, based on what I've seen, falls in the 55 to 70% range. So this is net energy that is put into the system to the thermal energy that hydrogen is carrying out for the net amount that is produced from the process. And these still have to be scaled to the scale that the current SMR technologies are being. In some ways, these are modular, so you can scale them easily. That's basically the discussion, but we still have to see how, for very large scale levels of production, how they match with the current existing technologies. The costs here are a lot more variable for electrolysis. This is from IEA, International Energy Agency, and fairly recent report as well. And as you can see, the spread depends on the type of electricity and where it comes from. But it's generally higher than reforming, more in the $2 to $3 per kilogram range. And then in Europe, because the energy costs are a lot higher, the costs of producing hydrogen are higher as well. Okay, so that's about how hydrogen is produced. It needs to be pipelined to either the storage site or for end-use purposes. And currently there are 1,600 miles of pipelines, mostly in the Gulf Coast, on the Gulf Coast side, because the concentration of production facilities were in that region. But the facilities are basically located close to production. So for example, a refinery in a sister location might produce hydrogen maybe a few miles from where the refinery is, and then use it in the refinery itself for hydrotreating, for example. Or a fertilizer plant would produce something within an auxiliary facility and then use it within a few miles of the plant. So large distance hydrogen pipelines are still not very common. Mixed hydrogen, so with natural gas transport, is really moving quickly to large scale commercialization. And concentrations in these range from 1% to 30% in demonstrations and deployments. They are not increased to higher concentrations, of course, because the production is somewhat limited of hydrogen. And the challenges of transportation because of steel embrittlement of the steel pipe that it may be transported in. You have to be a lot more be cognizant of leak control because it being a much smaller molecule than methane. And then hydrogen compression is another challenge that has to be considered, highly energy intensive. But there are some newer methods being proposed for pipelines as well. Fiber reinforced polymer pipelines, as FRM pipelines, have been proposed as possible alternative to steel, which are again not commercial yet, but 20% less expensive than steel pipelines, which can be several million dollars per mile installation costs. And then when it is not used immediately, hydrogen must be stored. So unless used at the production site, hydrogen must be stored. Large-scale surface storage continues to be challenging. There are several new technologies that are being developed, but these are again for more smaller end-use purposes as compressed gas or liquefied gas. This you see a large cylinder here with liquefied hydrogen in a commercial facility. And then there are several technologies, absorbent, liquid organic, these different types of materials that would then hold larger amounts of hydrogen per cubic meter of storage or per kilogram of the material that is being used. The more common are the commercial technology for storing hydrogen is the subsurface storage of hydrogen, underground storage of hydrocarbons in salt caverns. For example, the SPR or the Strategic Petroleum Reserve, some of which are shown here, most are on the Gulf Coast here in Louisiana and Texas, is very common. So petroleum products are stored here, petroleum crude oil is stored as crude oil. There is a facility here in Delta, Utah, has 2 salt caverns that store light petroleum products. And currently they are thinking about using similar storage for hydrogen. And hydrogen storage in salt caverns is less common than hydrocarbon storage, but is a proven technology. And I show you several places around the world where large amounts of hydrogen are stored. So the storage can range from 1,000 metric tons to 20,000 metric tons, can be fairly large amount of storage because the salt caverns are massive. They typically are 100 to 300 feet in diameter and 1,000 to 3,000 foot deep. So for those of us who work in porous media type flow or porous media type research, these actually are basically not porous media. Water is used to leach out the salt and create basically a big cylinder, high pressure cylinder, which is, as I said, is fairly massive, that is then used for hydrogen. So a very fascinating technology. And again, the only thing is that geographically and geologically, these are not as widespread, right? So we'll run out of salt cavern storage not fairly quickly if hydrogen economy does come into being. And so we'll have to think about other types of subsurface storage possibilities for hydrogen. And there are many in that regard. And then once it is stored, then it is used in power generation. It's kind of a central proposed use for stored hydrogen. But then there are lots of other uses, fuel cells in hydrogen vehicles, for making synthetic fuel. So you can combine hydrogen back with CO2 to make methanol or some other fuels. So for example, if you take hydrogen from biomass and then combine it with CO2, you essentially are creating a circular process there. It needs to be understood, though, that every conversion step, no matter how we envision it, will require energy. So there are going to be efficiency losses at every stage that we need to consider. Anyway, so then there is ammonia as also becoming a fairly significant part of our discussion now, even as a storage for hydrogen medium, refining metals and other. And this particular sector, at least in my judgment, is seeing transformative growth right now. There is a lot of incentives for converting current high energy use devices and systems to using hydrogen. So this is seeing big growth right now, and then the supply will have to keep up with that growth. So what about hydrogen power generation? So this is, as I said, one of the big end users that is being considered. Again, right now, there are not very many large-scale power generation facilities. So lots are in development. There again, as I mentioned, there is one in Delta, Utah, where we are going to see in just the next few years about 250 megawatt generation by a mixture of hydrogen and natural gas. There is a plant in Japan that uses a mixture of, it's a 20 megawatt small power plant. The power plant also have thermal efficiencies, right? So now you have made hydrogen from whatever source you made it from. And if you make electricity from it, it's going to have a thermal efficiency of about 60%, very similar to natural gas. It has potential to go higher, but right now, the current data indicates that it will be in the 60% range. So with all of from a thermodynamic thermal efficiency point of view, the round trip efficiency then for power generation would be essentially combination of these efficiencies that we're talking about, en route making power from hydrogen, and it's going to be 30% or less, maybe in the 20 to 30% range. So that is something that, again, we need to understand, because energy does have lots of uses. And if you decide to make hydrogen from energy, then and then power from it, this is what we will end up doing from an energy perspective. It might still be cost effective depending on what the cost structure is and what the incentives are, but from an energy point of view, that's what we may be looking at. There has been also a significant debate about water use over the life cycle of this particular contemplated use for hydrogen generation, electrolysis, storage, power generation back to electricity. And in this, we have a fairly detailed report on that, and we are happy to pass this on to anybody who is interested. So this is water consumption, gallons per megawatt hour, at the different cycles of this process. So operation is where you are essentially combusting hydrogen, and this is where most of the water requirement is, where you're cooling your systems to accommodate the turbines and so on. So this accounts for most of the water use. If the fuel that is used for generating the primary electricity is renewable, if it is wind or solar, or something similar, then you have a water footprint, which we'll probably have to think more about, especially in the West here, but also worldwide, of about 400 or so gallons per megawatt hour. So how does this compare with other energy sources currently in use? So here is hydrogen, but this is zero carbon or low carbon hydrogen. And then here are other energy sources. So this is natural gas without CCS. The most common method of producing electricity right now is 219. So the difference here is basically process for generating hydrogen, which is electrolysis. So the difference in here and here, but this comes with CO2, this comes without CO2. So if this also comes by CO2 capture, then it starts comparing with hydrogen, as you can see here, from a water use perspective. And then coal, because of its complexity and cooling requirements is higher. Coal with CCS is even higher. And then hydroelectricity, of course, you cannot compare really because it's a very different type of a system for comparisons. So at EGI, we are looking at several aspects of the hydrogen, mostly from a subsurface perspective. We have large geologic data systems offshore as well as onshore, and we're making use of this to figure out the geological attributes for natural hydrogen accumulation worldwide. So that atlas is being created as we speak. And then, as I said, we are going to run out of salt caverns if this continues to grow. And then we are also looking at hydrogen storage, again, making use of our extensive geologic knowledge and database. We do have research ongoing in renewables. We are home to Utah Forge. And so looking at energy integration and efficiencies to make hydrogen from various sources, and then looking at optimizing processes for water use and other purposes. So these are all ongoing things, including separation of CO2 for the various processes and storing it, because we have a very large CO2 storage group here at EGI as well. So just looking at it specifically, we are looking at natural hydrogen potential worldwide, evaluation of geological attributes and creating maps and a worldwide atlas. And the hydrogen subsurface storage beyond salt caverns, as I mentioned. Hydrogen production from a water energy optimization perspective, CO2 capture when hydrogen is produced, and CO2 storage near SMR facilities is something our storage teams are working on extensively. And so for the storage, subsurface storage beyond salt caverns, here are some of the things that we are looking at, and we would be happy to talk to you on that. In my home department, there are other faculty who are working on hydrogen research as well. I mentioned Professor Vitti, who has significant research effort in biomass to hydrogen. With him, Professor Niagara works on catalysis. Professor Gao works on electrolysis and developing better electrolysis methods and combining it with, for example, desalination and other considerations. So this is another big effort that is moving forward. And then there is some hydrogen combustion research in our department as well as in mechanical engineering in the college. We are also unfolding this new resilient energy program at the University of Utah with 5 courses, alternate energy and renewable energy. So this particular course will have a significant hydrogen component. So will this Geoscience for energy transition, which will be taught by. So these 3 courses will be taught in fall, and then these 2 will be taught in spring. So there's a multi-department course in the Price College of Engineering, and our home department, my home department, chemical engineering, will be offering a couple of the courses in this program. So in closing, I just wanted to point out that a large hydrogen economy already exists. As I mentioned to you, current production about 100 million tons per year. Use of hydrogen carrier, even though may not be energy efficient or cost efficient at this particular time, may be required to stabilize the renewable energy supply and grow the low carbon energy economy. And to do this, large-scale storage of hydrogen will be necessary. So we'll have to look beyond salt caverns and other technologies to make that happen. Hydrogen generation is an energy-intensive process. Most common process is a fairly optimized process right now with heat recovery and all that is reforming. But we'll need associated carbon capture, and there are very few facilities around the world currently that are doing this. Round-trip efficiencies for power generation using hydrogen. This is without carbon capture, or about 30%. With carbon capture, probably more to about 20%. Several research challenges still exist in extending the use of hydrogen, but based on what we are seeing right now, it is poised to see significant growth worldwide. So with that, I will stop, and I'm happy to take questions. Thank you.
Hey, Milind, this is Rob. Hey, I had a quick question. So down at the Delta site, where with the Mitsubishi Hitachi, I guess, turbines, they're going to be mixing natural gas fuel with hydrogen.
Yes.
What's the maximum amount of hydrogen that can be mixed? Or can it go all the way to 100% with those turbines, or is there a maximum about 30% or 40% that can be reached in terms of the amount of hydrogen that can be mixed in with the natural gas?
I think they aim to go to, but I think they're 100%. Currently, yeah, they're starting with something in the range of 25 to 30%. Off the top of my head, I'm not sure what the Japanese plant, the commercial facility, is doing. So it's a Mitsubishi technology, which is being used in Delta as well. But I think they're pretty confident that with the materials development on turbines for hydrogen, they will be able to do fairly close to 100%, if not 100%, maybe 75, 80% hydrogen by 2030.
Thanks.
That's a good question, Rob. Thank you.
Milind, can I ask a question here? This is Sid Green.
Thanks, Sid. Yeah.
I think the reason the world is looking at hydrogen and very interested, and indeed hydrogen is receiving a lot of attention right now, is that we're looking for a lower emissions energy source. That's the whole idea of hydrogen, as I understand it. It's not that we're looking for a new energy. We're looking for a new lower emissions, that is, for the world. So shouldn't some of the research, or maybe a lot of the research, be focused on how the emissions stack up and what research is needed to try to lower those emissions? Because that's what hydrogen is all about. And so shouldn't the emissions be a high priority in studying and research and teaching classes?
Emissions from other sources or from hydrogen itself?
The emissions reduction that would occur by moving to hydrogen.
Yes. Yeah, I think
that's the reason the world's looking at hydrogen, the whole idea is to lower emissions, carbon dioxide emissions.
Yeah.
So should we be looking hard at that to see what research is needed to reduce those emissions, or is it even possible?
Right. Actually, in this report that I shared just now, there is a CO2 equivalent, or at least the life cycle of SMR and then followed by CCS. So there are, but it's a good angle to look at. So apart from efficiencies and cost, you can also look at overall CO2 generated over the entire life cycle of the process. But also just not CO2, right? One challenge with hydrogen might be that it does operate, of course, higher temperature processes. And so NOx would still be a consideration that will have to be looked at. And I have seen a couple of papers in that regard, but not a lot of details. So I think comparison of emissions other than CO2 will also have to be considered, I think, when you start looking at widespread use of hydrogen. But that's a good point, Sid.
Yeah, very nice overview. Thank you very much.
Okay, thank you.